Welcome to The Explainer. Today we're going to tackle a really cool kind of AI. It's all about bridging that gap, between how we think and how computers think. We're going to see how a machine can actually understand our vague everyday language and turn it into something concrete, something it can actually act on.
So think about this for a second. How often do you say something is good or that it's almost time for dinner? All the time, right? Our language is just full of this stuff. It's nuanced. But computers? They live in a world of black and white, zeros and ones, true or false. So the big question is, how on earth can a machine possibly get a handle on these fuzzy human ideas?
Well, the whole secret is to move past that rigid, old-school binary logic. In that black and white world, a credit score of 749 is a world away from 750. One number means no loan, the next one means yes. It's this incredibly harsh cutoff. But fuzzy logic, it looks at that and says, hang on, those two scores are practically the same. It works with degrees of truth. It sees all the shades of gray that, let's be honest, make up the real world.
And that, my friends, is where fuzzy logic comes in. It's the solution. Think of it less like an on-off switch and more like a dimmer. It gives machines a way to reason with all those vague, subjective ideas we humans throw around constantly. And you've probably already seen it in action without even knowing it. It's the brains behind things like your car's anti-lock brakes or a fancy washing machine that just knows how dirty your clothes are.
So at the core of all this is something called a fuzzy inference system. And what's so amazing about it, and this is the key part, is that you don't need to be a math genius to build one. You can literally just take expert knowledge, human intuition, and write it down as a set of simple, easy-to-read rules.
All right, so let's walk through how this whole thing works. We're going to start with the problem with precision, then introduce fuzzy logic. From there, we'll see how to go from words to numbers, apply some human-like rules, and then, finally, get a nice crisp answer. We'll wrap up with the big picture, and to make it all super clear, we're going to use a really simple example, figuring out how much to tip at a restaurant.
All right, let's get into it. Step 1 is called fuzzification, and it's exactly what it sounds like. It's the process of taking our nice, precise inputs, think of a rating you give on a survey, and making them, fuzzy. We're translating them into a language the system can actually work with.
Okay, so let's set the scene. You've just finished a meal. You thought the service was pretty good, so you give it an 8 out of 10. The food, it was good too, let's say a 7 out of 10. These two numbers, the 8 and the 7, are our starting point. They're what we call crisp inputs.
So now, we have to define what terms like good or delicious actually mean to the computer. And we do this using something called membership functions. It sounds technical, but the idea is simple. Imagine you asked 100 people, on a scale of 1 to 10, what's good service? You wouldn't get one single answer, right? You'd get a range, a cluster of answers that you could plot out as a curve. That's a membership function. And by creating these overlapping curves for poor, good, and excellent, we're acknowledging that a single rating can kind of belong to more than one category at the same time.
Okay, so check this out. When we pass our numbers through these membership functions, this is what we get. That service rating of an 8, this system now sees it as being about 15% good and 38% excellent. And the food rating of 7, that's 55% fine and 45% delicious. See what happened? We took these flat, single numbers and gave them depth. We've added that human-like nuance.
All right, on to step 2, inference. This is where we take our new fuzzy numbers and start applying some good old-fashioned common sense.
Now this is the part that feels really human. We can write rules in plain English. For example, a rule could be, if the service is excellent or the food is delicious, then the tip is high. It's how we think, right? It's logic we use every single day.
And this is the really clever bit. The system takes those words we understand, or and translates them into super simple math. For or, it just takes the maximum of the two values. For and, it takes the minimum. It's such an elegant little trick for turning our intuition into something the computer can actually calculate.
So we run our fuzzy numbers through these rules, and each rule gets what we call a firing strength. You can think of it as, how true is this rule right now? So the rule for a low tip, well, the service and food weren't poor or rancid, so its strength is 0. It doesn't apply at all. The average tip rule, that was based on good service, which had a value of 0.15. So that's its strength. And then the high tip rule, remember that was excellent service or delicious food. It takes the max of those two, which gives it the strongest firing strength of 0.45.
Okay, time for the grand finale. Step 3, defuzzification.
We're going to take all this fuzzy stuff and boil it down into one single concrete number that we can actually use.
So here's where we are. Our rules have given us a fuzzy output for the tip. It's 0% low, 15% average, and 45% high, which is great, but you can't exactly write average 0.15, high 0.45 on a receipt, right? We need a real number. And to get that number, we use a really neat method called the centroid method. Basically, we take those original shapes that defined our tip amounts, low, average, high. We clip them down to size based on the firing strengths we just calculated. Then we mash all those clipped shapes together to form one new combined shape. And the final answer? It's just the center of gravity of that new shape, the exact point where it would perfectly balance if you put it on your fingertip.
And boom, there it is. The balance point, the centroid of that shape, gives us our answer, 20.2%. How cool is that? We started with vague feelings about good service and delicious food, applied some simple rules, and we came out with a totally precise, actionable number.
Okay, so let's take a step back and look at the big picture. Yeah, we built a tip calculator, but what we've really done is create a whole system. A complete, deterministic system that can take any set of inputs for service and food and map them to a specific output. And here's where it gets really powerful. If you plotted out the tip percentage for every single possible combination of food and service quality, you'd get this incredible 3D landscape. This is called a control surface. And this surface, this is our model. Now you can just pick any point on the service and food axis, look up, and the surface tells you the exact tip.
This is a huge deal for real-world applications. Think about it. When you're designing the system, the fuzzy rules are amazing because they're so easy to understand. An engineer can just sit there and tweak the rules in plain English. But all that calculation can be a little slow for something that needs to react instantly, like in a car. So what do? You take that beautiful control surface and bake it into a super fast lookup table. You get the best of both worlds: intuitive, human-centered design and blazing fast performance when you need it most.
And that's really the heart of it. The true power of fuzzy logic isn't in some crazy, complex math. It's the opposite. It's in its simplicity. It's the fact that you can build and understand a complex system using the same kind of gut-feeling, intuitive rules that we all use every single day. That's what's so revolutionary.
So I'll leave you with this question. In a world where AI is getting more and more complex, more like a black box that we can't understand, fuzzy logic offers something different. It offers transparency. So what if you could teach a machine not just by feeding it mountains of data, but by using your own intuition and experience? It's a pretty powerful thought, isn't it? It points to a future where we have AI that's not just smart, but also understandable. A future where we can genuinely trust and work with our machines instead of just telling them what to do.